Now it's time to talk about the standards behind the modern container images. Container image format specification, or in short, image spec, is the part of OCI that defines what container image is. Examining this specification is the way to understand how container images are structured and how they work. Our plan for this lesson is to take a real container image and then look inside it while at the same time examining the specification. This time, instead of using an Alpine image, let's use an HTTPD image. First, let's get an image in the OCI format. Scopio supports two OCI storage types. Archive is the image inside, or just the image. We will use the latter one. We run Scopio copy from the Docker source storage to the OCI destination storage. To better understand the structure, let's copy the previous version as well. Both commands copy the image contents into the HTTPD directory. The first file we are going to examine is called index.json, which lies at the root of the HTTPD directory. Index file points to one or more index manifests, as indicated by the media type field. The most interesting part here is an annotations block. That's how image tags look like inside image spec images. Note that there is not even a tag word in there. The tag is just a simple annotation with a reference to some name. When you work with tags in Docker or any other tool, keep in mind that in the underlying image implementation, tags do not exist. It's just some metadata that we are used to have. In the case of the HTTPD image we have here, the only other fields we have is the digest and the size. If you look at the specification, you will see that index file can also specify for which platform each manifest is valid. The same image could be used for both Linux and Windows. The digest part is the way image spec handles dependencies and addressability of different content types. Digest consists of the name of the algorithm used to get the digest and the digest itself. In theory, using the digests allows the tools that implement image spec to verify the content itself as long as the digest was received in a secure way. We saw the first content type image contains, the image manifest. We can find the manifest itself inside the blobs directory. This directory has one subdirectory per algorithm name used to get the digest of the content. In our case, SHA-256. Inside SHA-256 directory, we will find the list of files with hardly readable names. Each file name in this directory is the digest of the content of the file itself. For example, let's take the digest of the first image manifest in the index file and try to find this file only by its digest. We got an image manifest contents. If we now get a SHA-256 checksum of this file, we will get the file name. We do it by piping the file contents to the SHA-256 sum binary. These digests, of course, are not meant to be read by humans. This convention is handy for various container tools that are compatible with ImageSpec, because it allows them to verify checksums as well as discover required files by using those digests. Let's now examine the image manifest. I will cut the file and pipe it to JQ for a nicer output. Two main sections of the image manifest are config, which points to the image config file, and layers, which points to all the image layers for this particular manifest. Notice how each block has the size, the media type, and the digest. ImageSpec defines the same way to address content via digests, regardless if it's a config file or an image layer. Let's look at the config. We need to grab the digest and simply look inside the file. If you remember the previous video, where we looked at how Docker stores an image, then this file will feel oddly familiar to you. This config specifies for which platform this image is when it was created and different options that will be passed to container by default, like environment variables, command to execute, working directory, and exposed ports. It also has a history of changes to this image.
Do you think your project infrastructure is well set and maintained? We know for sure there is always room for improvement. If you are uncertain where to begin, let's first do an audit of what you already have. We will review your setup from every angle, performance, cost, security, high availability, automation, and provide you with a detailed roadmap of which direction your infrastructure should go, generate concrete tasks for you to implement, or even take on your infra entirely, if you let us, of course.
Image spec was largely inspired by Docker image specification. It took its best parts and then improved upon them and made it more generic and applicable to more use cases. Every field in the image config is defined by the image spec. What we see in this file is just a subset of what you can use here. When you build an image from a Docker file or a container file, many options you specify there will end up in this config file. Finally, let's look at the image layer. Let's get back to the manifest. Layers come in order, with the first layer being the base one and everything else is layered on top. The media type field tells us that each layer file is a gzipped tar archive, so to look at it, we need to unpack it. Let's do this for the base layer first. This looks like a complete file system, which seems about right because we do need a complete file system to run a container. Now let's look at the next layer. This layer has only some changes to the user directory. The most interesting part here is that there are no actual files except a strangely named .wh.wh.opq. This is a so-called wipeout file, as also defined in the image spec. Wipeout files are needed to remove some files from the image. When some container image tool is building an image, it needs to work with the layers. But if you just layer things one on top of another, then how do you remove files? The answer of image spec is those wipeout files. If you prefix a file with .wh, this file will be removed from this layer. And if you add a file called .wh.wh.opq, then every sibling directory or file in this directory will be removed. If I simply unpack each layer one after another with the tar command, none of the files will be removed. What is important to keep in mind here is that image spec only defines what wipeout files are and how to process them. You need an OCI compliant image building tool to process those wipeout files and to properly put layers on top of each other. Besides wipeout files, image spec defines complete process how layers should look like and how the container image tool should work with them. Let's recap quickly the most important things about image spec. Image spec defines how container images are structured and different config files inside the image. On the top level, you have an index file that points to multiple image manifests. Each manifest can be annotated with what we would call an image tag. Image manifest points to an image config file and to image layers. Image config file, in turn, defines how to run this image by specifying which command to run, with which environment, and so on. Image layers are just tar archives that need to be layered on top of each other by a container tool. Finally, all the files inside the image are referenced by digests and named after digests, except the index file. This structure is at the core of how container images are built, updated, and configured, at least in OCI compliant tools. But the truth is that to run a container, you don't need a container image in the first place. Instead, you need a container bundle, which will be the topic of our next video.